Okay, so we finished up Unit 1 yesterday, so today we're starting Unit 2. We begin Unit 2 with a little bit of discussion of measurement. Measurement actually started from a need to communicate. For example, let's say that you and I are both trying to build something. If we're in the same room and we're trying to build something exactly, we're both building the exact same thing, and you want to know how big something is, I can just, hey, it's this big, or I can walk it over to you and you can copy it or whatever. But let's say you're across town or down the hall or whatever, and we need to communicate it. I mean, I suppose I could always cut a piece of string or something that's that length and send it to you, but that gets to be wasteful. It'd be nice to have some way to just tell you how big it is, or write it down on a piece of paper and label it. So if I'm looking at my computer monitor here, I might take like this pen and say, okay, it's 1, 2, 3 pens wide. But I'm making a big assumption there. One is I'm making the assumption that you have a pen and that your pen is the same size as mine. Because if this is my pen and this is your pen, there's going to be a bit of a difference there, isn't there? So what they did was they chose things that pretty much everybody had and were pretty close to the same size. For example, your thumb, your hand, whatever. Parts of your body. The thumb is actually the origin of the inch. So let's say, so you can see it better, I'll measure my pen here with my thumb. So it's from the point of the thumb to the bend of the first knuckle here, the tip of the first knuckle here. So 1, 2, 3, just under 4 inches, or at least 4 of my thumbs. Now you might be thinking, well, people have bigger or smaller thumbs, but there really isn't as much variation. They're pretty close to the same size for the most part. And you also got to remember back then that people were a little bit smaller, so it wasn't as big of a difference. So they had to have that little bit of communication. So then how did they end up doing the measuring systems we have today? Well, we'll talk about the actual measurements, the inches and stuff like that in one of our next classes. But for right now, we want to put it together and look at the measuring devices themselves that they came up with. Eventually, instead of, like you saw me with my thumb moving it across the pen, it was tedious and slow to count like that. So eventually they came up, they took a stick, and they used their thumb and they marked it off. And they numbered it. So then they could take objects and they could just compare it. They could put one end of the stick at one end of the object, and the object would come out like that. And they'd say, okay, well, that's closer to 2 inches. Put another object on there. That one's also closest to 2 inches. Well, maybe not quite, barely close to 2 inches. So looking at those, are those 2 objects the same size? No, they're not. The green one is obviously longer, but on this measuring device, they're both measured at 2 inches because that's what they come closest to. That's what we call precision. Precision is the ability to distinguish between 2 things that are close in size or close in characteristics. This measuring device, this ruler, is not precise enough to tell the difference between the green and the blue line. So what did they do to make it more precise? Cut everything in half. Why did they cut everything in half? We might be wondering, why did they do halves, quarters, eighths instead of something nice and neat like tenths like they did with the metric system? Oh, no, it wasn't necessarily that. It was the fact that it's easy to cut something in half. You just take a piece of paper and fold it, and you've cut that length in half. It's easy to mark out halves. Fold it again, and you've got fourths. Fold it again, you've got eighths. So that's why they kept cutting things in half, or they ended up with those units, because they kept cutting things in half and ended up with halves, quarters, eighths, and so on. So now that I've cut these in half, pretend those are centered and evenly spaced. The blue line and the green line are both still closest to 2.5. So even though it's now more precise, it's still not precise enough to distinguish between the green and the blue line. So they would cut it in half again, give me quarters. And now you can tell the blue line's slightly closer to 2 1/4. The green line is definitely closer to 2.5. So now this device is precise enough to distinguish between those two. We refer to that as the degree of precision. The degree of precision is just the smallest division on the ruler. So this ruler is precise to 1/4 inch. It has a degree of precision of 1/4 inch. Now you'll notice the blue line is not exactly at 2 1/4, is it? But it could be anywhere from here to about here and still be counted as 2 1/4, couldn't it? How far away from that could it be and still be counted as 2 1/4? Yeah, and how far would that be? Well, 1/8 of an inch, right? If this is 1/4 inch between markings, halfway there would be 1/8 of an inch, right? So our possible error, or the built-in error in our measurement, which is half the smallest division. So in this case, 1/4 divided by 2, or 1/4 times 1/2 is going to be 1/8 of an inch. So since this ruler has a degree of precision of 1/4 inch, any measurement that it is used to measure could be off by up to 1/8 of an inch, even if it's used absolutely completely correctly. So one of the first things we need to be able to do is to determine what the degree of precision of a ruler is. And we do that by figuring out how many divisions there are in 1 inch. So if I'm going from 1 inch to 2 inch here, I got to count how many spaces, not lines. But I don't necessarily have to count the whole way. Usually the 1/2 inch is pretty easy to identify. A lot bigger mark. So all I have to do is count 1, 2, 3, 4, 5, 6, 7, 8. So how many are there in a whole inch? 16. So that means each division is 1/16 of an inch. That is my degree of precision. What is that possible measurement error then? A 32nd. Very good. 1/2 of a 16th. 16th divided by 2 is 1/32. So if I measure something with this ruler, and I state that it measures 2 5/16 of an inch. Technically, because this has a possible error of a 32nd of an inch, that is plus or minus 1/32 of an inch. Which means that could be 2 5/16 minus a 32nd would be 2 9/32. 2 5/16 plus a 32nd would be 2 11/32. So this measurement, even though it's stated as 2 5/16, could really be anywhere from 2 9/32 to 2 11/32. Does that make any sense? So for this measuring device, I want you to determine the degree of precision that built-in measurement error, and if something measures 4 3/4 inches, find the range of measurement. Careful. So we've got an obvious half-inch mark here, right? 128? Careful. I don't think I put that many marks in there. In fact, I'm going to do this. There's an obvious 1/4 inch mark right there. So let's just count those. 1, 2, 3, 4, 5, 6, 7, 8. Times 4 would be 32. So 1/32. So what's my possible error? 1/64 of an inch. Very good. Plus or minus 1/64 of an inch. So the 4 3/4, what's its range going to be? Well, this is how many 64s? 48 64s, right? So it ranges from 249. Very good. Make sense? Okay. Now, in woodworking and stuff, this is the way they usually measure stuff out. For you guys in CNC, it's usually done either decimal inches or it's done in metric. Now we can get into the big debate over metric versus standard measurement. What's more important? And I'll be perfectly honest with you guys right now. 70 to 80% of what's manufactured out there right now is still done in standard measurement, but it's not going to stay that way. Now, when I was in middle school, my middle school science teacher stood up in front of the room and was preaching to us, within 10 years, the United States is going to be totally switched over to the metric system. Some of you may have had the same speech given to you. Well, not to give too much away here, but it's been a little more than 10 years since I was in middle school. Probably more like 30 years. But hasn't happened yet, but it will happen. But I'm not going to tell you that it'll be 5 years or 10 years or whatever. We're a little slow when it comes to transitions like that. But right now, if you were to try to buy gunpowder or alcohol or tobacco, you can't buy a pound pouch of tobacco anymore. Everything that is regulated by the ATF is required by federal statute to be bought and sold in metric units. What's happened is the United States has allowed each regulatory agency to make their own decision when they switched over. The ATF did that back in the 90s, made that changeover. And since then, you can't buy a 5-pound keg of gunpowder anymore. It's a 2.2 kilogram keg or whatever. Probably the next agency to go is going to be the FDA, by the way. You see all your food is already labeled in ounces and milliliters and stuff like that. It's already dual labeled. It'll change over relatively soon, I think. But anyway, the transition will come. A lot of your international companies have made the transition. IBM did it about 4 or 5 years ago. Even things that are produced in the United States are done in metric. And they figure it's saving them between $10 and $12 million a year to make that switch. Because otherwise, whenever they designed something, they had to design it in both standard units and then convert it over to metric units so that their foreign suppliers knew how big to make it. And then you had the problem with, okay, when it's converted into metric from standard, there's round-off errors, and now they don't quite fit as well. And there's a tremendous amount of money they figured they were going to save, probably more than that in the long run, by just using metric units for everything. So anyway, you guys are going to be dealing not with the fractions, the 1/4, 8ths, and 16ths and stuff. You're going to be dealing with decimal units. So the question comes, let's say you have a part that is measured 1.2 inches. Does it matter whether you write it like that or this? Are those the same measurement?
They are, but the one on the right is 1 per second.
Okay, yeah, it's kind of a trick question. They are the same measurement, but they're implying something a little bit different. This one is implying a certain amount of precision. This one here is implying that you had a ruler capable of measuring to the nearest tenth of an inch, and this object that we're measuring was closest to the 1.2. In other words, this is a plus or minus. A degree is implying a degree of precision to the nearest tenth. Half of that is 0.05. It's implying a plus or minus of 0.05. So it's saying anywhere from 1.15 to 1.25 inches. This one over here is implying, I'm not even sure if I can draw this out tight enough to get those marks in there, but there's no way I'm going to get them all in there. This is implying that it measures down to the thousandth of an inch. Has a degree of precision of 0.001. But it still happened to be closest, somewhere in that range, to 1.2. It's got a plus or minus of 5/10,000ths, half of a thousandth of an inch. So this is implying a range of anywhere from 1.1995 to 1.2005 inches. Quite a bit narrower range than that one. This is something we call significant digits. The significant digits tell us something about our measurement. Now, the word significant can be a little bit tricky because the things we're looking at here are all important. We're used to the word significant meaning important or useful. All the digits are important, but significant means they are significant to the measurement. They mean something to the measurement. For example, if this is inches, in this measurement, this 0 right here, is it important? That's very important. Without that 0, it changes the whole meaning of the 7 and the 5, doesn't it? Is it necessary to have that 0 there? Yeah, it is. If we take that 0 out, like I said, it changes the meaning of the 7 and the 5. It's not significant, though. It's not part of the measurement. This 0 here, however, if I took that out, would it change the meaning of any of the other digits? No, it wouldn't. It's not necessary numerically. The only reason to have that 0 there is if it's part of the measurement. So that 0 is considered a significant part of the measurement. When we're talking about significant digits, all non-zero digits are significant. So the 7 and 5 are automatically significant. Zeros are the tricky part. Zeros are only significant if they are what we call otherwise unnecessary. That's kind of a fancy term there, otherwise unnecessary. But what it means is if we could take those zeros out and it would not change the meaning of the number, well, then they must be there just for the measurement, so they become significant to the measurement. Or if they're between other significant digits. So for example, as we set up here, this 0 was necessary. It has to be there to give the 7 and 5 their place values. So it's not significant. This one, however, does not have to be there. It's not necessary otherwise. So it would only be there if it's part of the measurement. So that one is significant. So 70,500 pounds. Obviously significant, the 7 and the 5 are significant. How about this 0 right here? Yeah, it's between other significant digits. How about these two? If I took them out, would it change the meaning of the other digits? Yes, it would. Therefore, they're numerically necessary, which means they're not part of the measurement. Unless there's a third qualification. They're indicated. So now what on earth does that mean? There's another new rule. Well, let's look at that 70,500 pounds. That line under the 0 there indicates that it's a significant 0. What does that mean? That means this one here is being measured with a scale. This one's being measured with a scale that's only good to the nearest 100 pounds. I did that wrong. This should 7,400 and 600. You can only measure to the nearest 100 pounds, and it's happened to be closest to 70,500. This one here, because of this line here, is indicating that that one is able to measure to the nearest 10 pounds. Whatever scale we use to measure that is divisible. It can go down to the nearest 10 pounds, and we still happen to be closest to the 70,500. So this one has a degree of precision to the nearest 100 pounds, because that is that digit, the last digit that is a significant digit, which means it is plus or minus 50 pounds. Yes, sir? This should be 70, you're right, 70,000. There you go. This one here has a degree of precision of 10 pounds. So it's plus or minus 5 pounds. So the degree of precision becomes the place value of the last significant digit. Just throwing some numbers out here. This one here, of course, the 4 and the 1 are significant. Is that 0 significant? If I took it off, would it change the meaning of the other numbers? Yes. So it's necessary, which means it's not significant. I know that's confusing as heck, isn't it?
Necessary is not significant.
Well, I mean, it would be there. It would be there whether it was part of the measurement or not, is what I'm saying. So it has to be there as part of the number. So it's not, unless it's indicated, it's not part of the measurement. So that one has 2 significant digits. The number of significant digits we call the accuracy. So that one has an accuracy of 2 significant digits. The precision, what's the place value of that last digit? Tens. So it's precise to the nearest 10, which means the error would be plus or minus 5, right? This one here, the 2 and the 5 are significant. Is that 0 significant? If I took it out, would it change the meaning of the other numbers? No, so it's not necessary numerically, which means it has to be part of the measurement. The only reason it would be there is if it's part of the measurement, so it is significant. So that has an accuracy of 3 significant digits. The precision, what's its place value? 10. So the error is plus or minus 0.05, 5/100. This one, that is a decimal point there. So the 9 and the 7 are significant. Is this 0 significant? Yes. How about this one? Yeah. At the end there, being after a decimal point, I could take it off and it wouldn't change the other numbers. So the only reason to include it there is if it is part of the measurement. So that is precise, or has an accuracy of 4 significant digits. The precision is thousandth is the place value of that last digit. So that's a plus or minus 5 10,000ths, 5 tenths. Okay, up here, those 3 are significant. How about this one? Yep, this one? No. That one has to be there no matter what. Okay, if it's in front of the decimal point and at the end of the number, it's not significant unless it's indicated. So this has 4 significant digits. Precision is to the nearest 10, so it's a plus or minus 5. Like this one down here, I got a line under that one. So that one's significant. So here we've got the 5 and the 2. How about this one? This 0? Yes, because it's between the 5 and the 2. How about these? Well, this one here normally wouldn't be significant, except we have this one here, which is, because it's after the decimal point, and if I took it off, it wouldn't change the meaning of the other numbers. The only reason for that 0 to be there is it's part of the measurement. So since that one's significant, this one has to be because it's between digits. So we have how many digits? 5 significant digits. Precision? There's 10. So plus or minus 5/100. Now this one here, we got the 3 and the 2. This line is saying that that one is significant, which means this one is as well. That one, no. None of those 3 would be significant because they have to be there. So they're not part of the measurement, they're part of the number. But this one's indicated, so that's telling us that we really did measure to the nearest 10 inches. It just happened to be closest to 32,000. So that has 4 significant digits to the nearest 10, so it's a plus or minus 5. So I want you guys, for me quickly, to do for each of the numbers I'm going to list here in your notes quick, find the precision, the possible error, and the accuracy. Notice the number of significant digits. So for each of those, find those 3 items. Okay, so the 27,000 here. Let's start out with the accuracy. How many significant digits does it have? Just the 2. So the precision is the thousands. So the error, plus or minus 500 inches. You got it. So this next one, the 2, the 3, and the 1 are significant. How about this 0? Yes. This 0? Yes. Being after the decimal point back there, the only reason to include it would be if it was part of the measurement. So this is 5 significant digits. Precision, just 1,000. So plus or minus 5 10,000ths. This one here, the 9 is significant. We have the indicator, which means that 0 is significant. How about this one? Yep, because between them, this one, no. So you have the 3 significant digits. Precision, nearest 10, so error, plus or minus 5. And this last one, the 8 is significant. How about this 0? No, it's not. It's there because it tells us what the 8 is. It has to be there. How about this 0, however, is, because the only reason to include it is if it were part of the measurement. This is one example we hadn't gone over yet. If they're at between the decimal point and there's no other numbers in front of them, they're not significant. So that one is not. It has to be there to give the 8 its meaning. So this one only has 2 significant digits. Precision to the thousandth. Error 5 10,000ths. Does that make any sense? It's a different way of thinking, isn't it? A very different way of thinking. What I'm going to do is I'm going to have you guys start working on this. It's page 225 in the big book. Then I'm going to pass back your tests so you can have some time to finish those up quick. 1 through 20, the odds you can work on. That's exercise 7-6, I believe. Then I'm going to pass your tests back so you can have about 15 minutes or so here to finish those up.